Welcome back. We're finally using the Laplace transform to do something useful. In the first part of this problem, we just had this fairly straightforward differential equation. And I know it's a little bit frustrating right now because you're like, this is such an easy one to solve using the characteristic equation. Why are we doing Laplace transforms? Well, I just want to show you that they can solve even these problems. But later on, there are going to be classes of problems that, frankly, our traditional methods aren't as good as the Laplace transform. But anyway, how did we solve this? We just took the Laplace transform of both sides of this equation. We got all of this hairy mess. We used the property of the derivatives of functions when you take the Laplace transform. And we ended up, after doing a lot of algebra, essentially, we got this. We got the Laplace transform of y is equal to this thing. We just took the Laplace transform of both sides and manipulated algebraically. So now our task in this video is to figure out what y's Laplace transform is this thing. And essentially, what we're trying to do is we're trying to take the inverse Laplace transform of both sides of this equation. So another way to say it, if we could say that y, we could take the inverse Laplace transform of both sides. We could say that y is equal to the inverse Laplace transform of this thing, 2s plus 13 over s squared plus 5s plus 6. Now we'll eventually actually learn the formal definition of the inverse Laplace transform. How do you go from the s domain to the t domain, or how do you go from the frequency domain to the time domain? We're not going to worry about that right now. What we're going to do is we're going to get this into a form that we recognize and say, oh, I know those functions. That's the Laplace transform of whatever and whatever, and then we will know what y is. So let's try to do that. So what we're going to use is something that you probably haven't used since Algebra 2, which is, I think, when it's taught in 8th, 9th, or 10th grade, depending, and you finally see it now in differential equations that it actually has some use. Let me write it. We're going to use partial fraction expansion. And I'll do a little primer on that in case you don't remember it. So anyway, let's just factor the bottom part right here. And you'll see where I'm going with this. So if I factor the bottom, I get s plus 2 times s plus 3. And what we want to do is we want to rewrite this fraction as the sum of two, I guess you could call it partial fractions. I think that's why it's called partial fraction expansion. So we want to write this as the sum of a over s plus 2 plus b over s plus 3. And if we can do this, then and you might already, bells might already be ringing in your head. We know the Laplace. We know that these things that look like this are the Laplace transform of functions that we've already solved for, and I'll do a little review on that in a second. But anyway, how do we figure out a and b? Well, if we were to actually add a and b, if we were to, let's do a little side right here. So if we said that a, so if we were to give them a common denominator, which is this, s plus 2 times s plus 3, then what would a become? We'd have to multiply a times s plus 3, right? So we'd get a s plus 3a, right? This, as I've written it right now, is the same thing as a over s plus 2. You could cancel out an s plus 3 on the top and the bottom. And now we're going to add the b to it. So plus, I'll do that in a different color, plus, well, if we have this as the denominator, we could multiply the numerator and the denominator by s plus 2, right, to get b times s plus 2b. And that's going to equal this thing. That's going to equal, right, all I did is I added these two fractions. Nothing fancier than there. That was Algebra 2. Actually, I think I should do an actual video on that as well. But that's going to equal this thing. 2s plus 13. All of that over s plus 2 times s plus 3. Notice, in all differential equations, the hairiest part's always the algebra. So now what we do is we match up. We say, well, let's add the s terms here. And we could just say that the numerators have to equal each other because the denominators are equal. So we have a plus bs, a plus bs, plus 3a plus 2b is equal to 2s plus b. So the coefficient on s on the right-hand side is 2. The coefficient on the left-hand side is a plus b. So we know that a plus b is equal to 2. a plus b is equal to 2. And then on the right-hand side, we see 3a plus 2b must be equal to, what else? Oh, this is a 13. Did I say b? This is a 13. That's a 13. It looks just like a b, right? That was 2s plus 13. Anyway, so on the right-hand side, I get, what was it, 3a plus 2b is equal to 13. Now we have two equations with two unknowns, and what do we get? I know this is very tiresome, but it'll be satisfying in the end because you'll actually solve something with a Laplace transform. So let's multiply the top equation by 2, or let's say minus 2. So we get minus 2a minus 2b equals minus 4. And then we get, so add the two equations. You get a is equal to, these cancel out. A is equal to 9. Great. If a is equal to 9, what is b equal to? B is equal to 9 plus what is equal to 2? Or 2 minus 9 is minus 7. And we have done some serious simplification, because now we can rewrite this whole expression as the Laplace transform of y. The Laplace transform of y is equal to a over s plus 2 is equal to 9 over s plus 2 minus 7 over s plus 3. Or another way of writing it, we could write it as equal to 9 times 1 over s plus 2 minus 7 times 1 over s plus 3. Why did I take the trouble to do this? Well, hopefully you'll recognize this was actually the second Laplace transform we figured out. This was the second Laplace transform we figured out. What was that? I'll write it down here just so you remember it. It was the Laplace transform of e to the at was equal to 1 over s minus a. That was the second Laplace transform we figured out. So this is interesting. So if we were to take, this is the Laplace transform of what? So if we were to take the inverse Laplace transform, actually let me just stay consistent. So that means that this is the Laplace transform of y is equal to 9 times the Laplace transform of what? If we just do pattern matching, if this is s minus a, then a is minus 2. So 9 times the Laplace transform of e to the minus 2t. Does that make sense? Take this, put it in this, which we figured out, and you get 1 over s plus 2. And let me clean this up a little bit, because I'm going to need that real estate. I'll write this. I'll leave that there, because we'll still use that. And then we have minus 7 times, this is the Laplace transform of what? This is the Laplace transform of e to the minus 3t. E to the minus 3t. Right? It's just pattern matching. You're like, wow, you know, this if you saw this, you would go to your Laplace transform table if you didn't remember it. You'd see this. You're like, wow, that looks a lot like that. It's just, I just have to figure out what a is. I have s plus 3, I have s minus a. So in this case, a is equal to minus 3. So if a is equal to minus 3, this is the Laplace transform of e to the minus 3t. So now we can take the inverse Laplace transform. Actually, before we do that, we know that this, because the Laplace transform is a linear operator, and actually now I can delete this down here. We know that the Laplace transform is a linear operator. So we can write this. And you normally wouldn't go through all of these steps. I just really want to make you understand that what we're doing. So we could say that this is the same thing as the Laplace transform of 9e to the minus 2t minus 7e to the minus 3t. Now we have something interesting. The Laplace transform of y is equal to the Laplace transform of this. Well, if that's the case, then y must be equal to 9e to the minus 2t minus 7e to the minus 3t. And I never proved to you, but the Laplace transform is actually a one-to-one transformation. That if a function's Laplace transform, if I take a function and get its Laplace transform, and then if I were to take the inverse Laplace transform, the only function whose Laplace transform that is that original function. It's not like two different functions can have the same Laplace transform. Anyway, a couple of things to think about here. Notice, we had that thing that kind of looked like a characteristic equation popped up here and there, and we still had to solve a system of two equations with two unknowns. Those are both things that we had to do when we solved an initial value problem, when we used just traditional the characteristic equation. But here it happened all at once, and frankly it was a little bit hairier because we had to do all this partial fraction expansion. But it's pretty neat. The Laplace transform got us something useful. In the next video, I'll actually do a non-homogeneous equation and show you that the Laplace transform applies equally well there. So it's kind of a more consistent theory of solving differential equations instead of kind of guessing solutions and solving for coefficients and all of that. See you in the next video.